This particular problem, we have a 50 kilogram beam that is held in equilibrium by some tension T here, and that T is angled at 30 degrees. And part A wants us to find the magnitude of the tension in the cable, and then part B asks us if the cable is moved closer to the pivot at the midpoint, how will the magnitude of the tension cable be affected, whether increase, decrease, or remains the same, or unchanged. Alright, so let's crack this out. Let's do part A first. So to do part A, because it says held in equilibrium, I'm going to set up my torque in the clockwise equal to my torque in the counterclockwise direction. So let's go ahead and identify our forces here. So here, the weight of the beam is placed at the midpoint here of the beam. And that is F of G beam. F of G by definition is just mass times gravity. The mass of the beam is given here as 50 kilograms, so the unit kg implies its mass. So if we multiply that on a calculator, you get a value 498 newtons. This is just the magnitude of the weight. Okay. Other than that, here's tension. Tension is pointing towards the wall there, and then because it's pointing towards the wall, it has to have a component. Ty in this case will be T sine at 30. The angle given here once again touches the horizontal axis, so your opposite or your y component would simply be sine, and your adjacent will be Tx. Okay. So there it is. Ty is just T sine 30. Tx is just T cosine of 30. But once again, when you do torque, all you have to do is focus on the force that is perpendicular to your moment of arm. So here I'm going to cross out Tx because Tx parallels the beam. Anything that parallels contributes no torque. Okay. Other than that, here I have an F of G naturally that will cause the beam to rotate in a clockwise direction. And then if you pull up on this beam with Ty, it'll rotate in the counterclockwise direction. So here I have two forces that are placed at different distances on the beam, and that'll cancel each other out in terms of rotation. So let's go ahead and crack out torque here. Torque that is produced in the clockwise direction. For this particular diagram, that'll be due to the weight of the beam itself. So once again, if you cut the string, the beam will rotate in a clockwise direction. It'll go from, let's say, 3 o'clock to 4 o'clock to 5 o'clock. Well, we know F of G, we just need to figure out how far that is away. So here in the diagram that just came up, F of G is placed at a length of L over 2. I don't know what the length of the beam is. It wasn't given to me, so I'm just going to call it L, but midpoint of L would just be L over 2. And then I'm also going to identify on the right side, Ty is perpendicular to the beam, but it is placed at the very end of the beam. So I'm just going to call that length L. Okay, from the wall to the edge of the beam is just a length L. So once I do that, I have everything that is perpendicular. So watch my cursor. L over 2 is perpendicular to F of G. The length L here, my moment of arm, is perpendicular to Ty. So focus on stuff that's perpendicular and then just use that stuff. Okay. Here F of G beam is 490 because I already calculated. I left out the units here just to clean up my work a little bit. And then how far is it away from the pivot? The pivot being this area of the wall to the left here. And that is the distance of L over 2, whatever L is. And then Ty is simply T sine of 30. I identified that earlier. My Ty component here is pointing up, and that is equal to T, whatever T is, times sine of 30 degrees. And then how far is it away? So our cable, the moment of arm here, would just be the whole entire length because the pivot is at the wall. To go from the wall all the way to where Ty is, that would just be a length of L, whatever L is. Okay. So as you can see here, I don't know what L is. I don't know what L is on the right side, but it appears on both sides. So I'm just going to go ahead and cross it out. So we can simplify this down a little more. Sine of 30 is just a half. And then once you notice here, once you cancel out the L on the left side here, that parentheses just really reduces down to just 1 over 2. I see a 1 over 2 on the left side, a 1 over 2 on the right side. So I'm just going to go ahead and cancel that out. And therefore, and really the only thing that's left on the left side is 490. The only thing that's left on the right side is just T. So in this case, we just solve for T, and T is 490 newtons. Okay, so that is the magnitude for part A. Now part B asks us if the cable is moved closer to the pivot at midpoint. So here's the diagram, right? So instead of the cable being tied to the very, very far right endpoint, it is now moved closer to where the center, where the midpoint of the beam is. And it wants us to find, whether the tension in the cable increase, decrease, or stays the same. Well, let's go ahead and draw your stuff out again. F of G here for the beam is at the center of the beam here, which is 490 newtons. We already did that over here earlier. And then here's T. Okay, but in this case, I'm just going to focus my attention on TY. If you listen earlier, TX, why it does exist, it is parallel to the beam itself, so it contributes no torque, so I'm not going to waste my time here in this second diagram. I'm just going to go ahead and draw TY, and TY is placed there where the cable is touching the beam, and it's pointing upward, and TY, once again, is T sine at 30. The angle hasn't changed, it's just the placement of the rope or the cable that has changed, okay? So, the system is still in equilibrium, which means we have a clockwise torque, and that has to equal to a counterclockwise torque. So if I set this stuff up, here's the length of L over 2, just as before. But once again, the end of the cable is moved now. Instead of from the far right, it's going to move to the midpoint. So therefore, the length here is also going to be L over 2. And so watch my cursor. L over 2 on the bottom is perpendicular to 490. L over 2 on top is perpendicular to TY. So TY is going to cause the beam once again to rotate in a counterclockwise, and the weight of the beam in this diagram naturally will want to cause it to rotate in the clockwise direction. So you have a counterclockwise and a clockwise that will cancel each other out. So I'm just going to set it up. I'm just really going to carry my work down from here. Watch my cursor. So instead of writing everything else out, okay, so 490, which is the force, times the moment of arm, which is perpendicular to it, which is L over 2. And then Ty is simply T sine 30. And then how far is it away from the pivot? It is the length of L over 2. So as you can see here, L over 2 appears on both sides. So I'm just going to go ahead and cancel that out. Okay, and then sine of 30, once again, is a half in this diagram. So instead of saying sine 30, I'm just going to go ahead and substitute that out for 1/2. So to solve for t, all we have to do is multiply both sides by 2. So 2 times 490 will give us a value of 980. Okay, so as you can see here, the answer is greater than what it was before. So in this case, I would choose the value of increase. However, I did the math there just to show you that it does increase, but conceptually speaking, watch what I'm going to do in my work here in blue. Okay, you notice here I boxed the left side here because the weight of the beam hasn't changed. The distance from the weight to the pivot hasn't changed. So I'm going to say that this stays the same. Okay. However, Ty has T in it. Right? Ty is T sine theta. So really, essentially, we're asked to determine whether T itself goes up or down. Well, I can determine that just by looking at these functions. Well, I also know that our cable has gone down. Okay, so instead of placing it at the very end, it's now moved to midpoint. So I can make this conclusion: the left side, the clockwise torque, due to the weight of the beam itself, has not changed. F of G hasn't changed. The distance from F of G to pivot hasn't changed, so the whole entire left side stays the same. The R cable has gone down, so instead of a length L, it got moved to a length of L over 2. Well, in order for this left side to stay the same, if you reduce the moment of arm, the point in which the force is being applied to relative to the pivot, Ty has to go up. Well, if Ty goes up, then it implies T also has to go up. So if you look at this function over here where I'm circling back and forth, right? If Ty goes up, T also has to go up because sine at 30 is a half, which is a constant. So it's a direct relationship. So if one side goes up, the other has to go up. So we can say that if Ty goes up, therefore T has to go up as well. So how much, I don't know, but I know that it goes up. So this particular question B is more of a conceptual question. Okay, so I hope that makes sense. So if the left side stays the same and the length of the R goes down, Ty has to go up. If Ty goes up, then T has to go up to compensate for it. All right, but here's the next, I guess I call it a bonus question. I said, what if the angle theta is decreased, right? So instead of 30 degrees, what if the cable is attached to the wall at an angle that is less than that? You can go less or more. I just happen to choose decrease. Well, here, if you look at this particular function here, right, the left side hasn't changed, once again, okay? Well, how do you know if T increases or decreases if you change the angle? So instead of moving the length of the cable, what if you actually keep it at the very end of the far right, but you just lower down the angle? Well, Ty is T sine theta. So if the left side hasn't changed, the length of the cable hasn't changed. I mean, not the length of the cable, but the length away from the pivot for Ty hasn't changed. Well, in terms of the answer, or sine of 30, let's say you do sine of 30, and then if you do sine of, let's say, 20, as theta decreases, sine also decreases with it, okay? So if sine of theta decreases, and therefore to keep this side the same, t has to go up. So if this goes down, t has to go up to make sure that this stays the same on the left side, okay? So the final conclusion is that if theta decreases, therefore tension has to also increase to compensate for the fact that sine of a lesser angle is a lesser value. So if it's a lesser value, t needs to be greater, okay? If you need to, hopefully listen to that again. I hope that makes sense. All right, stay nerdy, don't be whack.